Politecnico di Torino is a leading institution for engineering, architecture, and design, distinguished by a strong commitment to academic excellence and innovation. With over 38,000 students from more than 120 countries, the university provides a truly international environment and offers 80-degree programs. It also supports over 950 research projects and has filed over 1,350 patents. By establishing partnerships with major industry leaders, Politecnico di Torino bridges research and real-world application, shaping the future of global innovation. For the TunReFit project, researchers from the Department of Structural, Geotechnical, and Building Engineering of Politecnico di Torino collaborated with Autostrada per l'Italia Group to turn a forward-looking idea into a practical application in the Olympia motorway tunnel in Italy.
We have been working for quite some time on the integration of geothermal exchangers into geotechnical structure as an action for mitigating global warming. By embedding pipes into elements in contact with the ground, like piles, retaining walls, tunnel linings, we can exchange heat with the ground, retrieving renewable energy. This is the concept of energy geostructures, and we have applied this concept to this particular project.
The Olympia Tunnel is located along the A26 motorway in northwestern Italy. It extends for 890 meters through a marly formation with a maximum overburden of 40 meters. The Olympia Tunnel has been operational since the early 70s, thus overcoming 50 years of service. On-site inspections revealed inner voids honeycombing, deterioration of joints, longitudinal cracks, most of which occurred during the original concreting phase. One of the relining solutions in the tunnel renewal strategy, promoted by Autostrada per l'Italia Group, was selected to renovate the tunnel, involving the partial replacement of the existing lining with a new cast-in-place reinforced one. Following pre-consolidation with fiberglass dowels, the original lining was milled, and the surface was then regularized through the application of sprayed shotcrete. An innovative waterproofing system comprising modular, pre-formed sheets was installed to ensure continuous protection against water ingress. After the pre-assembled steel lattice girders had been positioned, the new high-performance lining was cast in place using 6-meter-long arch shuttering systems.
The refurbishment works offer the valuable opportunity to incorporate the pioneering TunReFit project into the process, thus transforming the Olympia tunnel into an energy geostructure. Our previous experience with projects like Enertun, where we developed and installed energy segments in Turin Metal Line 1 for thermal exploitation, was key to the success of the project. We developed innovative sustainable solutions and patents for the thermal activation of existing tunnels while designing the application to the Olympia tunnel.
Following the partial demolition of the existing lining over the entire vault, 1,000 meters of PXA pipes with a diameter of 20 millimeters and 2.3 millimeter thick were arranged in a transversal meandering fashion along parallel hydraulic circuits. The pipes were embedded within the non-structural regularization layer between the existing and the renovated tunnel linings behind the waterproofing and drainage systems. A preliminary 2-hour water pressure test was successfully performed. During nail gun waterproofing, Velcro bands were placed between pipe branches to protect the pipes. Lastly, steel lattice girders were positioned and the intrados shell was cast in place. The heat harness through geothermal exploitation is transferred for anti-icing purposes to a 27-meter-long and 3.6-meter-wide stretch of the emergency lane outside the tunnel by means of insulated collectors running within the sidewalks. In summer, the same motorway section can collect thermal energy from solar irradiance to be stored in the rock mass. Outside the tunnel, pipes were installed transversely after milling the motorway pavement by 14 centimeters and connected to a smart hydraulic pump. A 5-centimeter thick concrete slab was poured to cover and protect the serpentine for the subsequent binder and wearing asphalt layer setup.
The geothermal energy harnessed by the innovative 14 meters long energy tunnel is utilized to prevent ice formation on the motorway surface. While ensuring road safety in winter, in summer the system captures solar heat from the road and stores it in the surrounding rock.
A comprehensive monitoring system was implemented to assess the thermal behavior. Transducers were installed to measure the temperature of the tunnel lining and the road pavement. To evaluate the amount of heat dissipated and harnessed through the system during operation, a flow meter, a pair of temperature transducers, and a heat meter were installed. The system is designed to operate automatically based on the monitored temperature of the motorway pavement. Whenever the temperature of the pavement goes below 4 degrees Celsius during winter and above 30 degrees Celsius during summer, this activates the system that heats up or cools down the motorway pavement. The system costs just €10,000, which is only 2% of the total budget for renovation. Despite this modest investment, the potential benefits are substantial. On a large scale, the geothermal anti-icing system would be markedly performing in mountain motorway stretches characterized by a sequence of tunnels and viaducts. For example, in the case of instrumenting a 9 kilometers long A26 motorway stretch, 6,500 meters of tunnels will be available to anti-ice the road pavement surface with a payback time of 13 years. Such a sustainable solution reduces the use of de-icing salts that accelerate pavement degradation, induce vehicle corrosion, and pose environmental risks to aquifers. TunReFit stands out as a first worldwide pioneering example of an anti-icing solar collecting energy tunnel-based system, paving the way for large-scale implementation of the technology.